Hi everyone. Now we are going to extend the coin case we saw in the previous video to the case with more outcomes. Remember that the coin case is going to work only for binary variables because we have heads or tails, in other words 0 or 1. But in general, we find categorical variables with many outcomes, right? For example, in geography, when we identify different regions, that's a categorical variable. Or if we have the brands of different products, that is a list of names, in other words, categorical variables with many outcomes. Or even if we have a continuous variable, we could create ranges and define, instead of a continuous number, any number from 1, 2, 3, 4, 5, 6, and that's going to be a categorical variable of 6 possible outcomes. So how we extend the previous model to work with this type of variables? Well, turns out it's very straightforward. Remember, all started with the Bernoulli distribution, that is the probability of getting a success after one flip, and we had 2 possible outcomes. Note that we could rewrite the same equation this way, which is exactly the same. The main difference is that instead of having theta and 1 minus theta, we have theta 1 and theta 2. But since theta 1 plus theta 2 must be equal to 1, for example, the probability of heads plus the probability of tails must be 1, then we know that at the end theta 2 is 1 minus theta 1. So we could use just one parameter, and with that we will know both. So we could write this equation this way or that way, and it will perfectly work. So let's stay with the second way for a while. How we extend this Bernoulli equation to more outcomes? Well, it's very straightforward, because in this case it's called the multinomial or categorical, and basically we just have more possible thetas from 1 to k minus 1, and we go and multiply each of those thetas to the power of the outcome. So we will see that all the time we flip and get one result, is only one theta, the one that will be 1, and the others will be 0, right? So in this case, instead of being the probability of getting a success in one flip, is the probability of getting the outcome m for any of the possible outcomes in one flip. So we will reduce our notation. Our list of possible thetas are going to be capital theta. And again, all of them are between 0 to 1. And since they add up to 1, we know that we only need k minus 1 theta, because the last one is going to be 1 minus the sum of all the others. So that's why we need only k minus 1, because they add up to 1. For simplicity, we will list all of them, okay, here. And we know that all of them are between 0 and 1, same as with the Bernoulli. And instead of having possible outcomes 0 or 1, we have from 1 to k. Okay, so now we know how our Bernoulli is written in multiple outcomes version here. What happens with the binomial? Remember, the likelihood in our beta case was a binomial distribution, which is very similar to the Bernoulli, and it was this equation. Now we will extend it to the multinomial case, in where we, instead of again multiplying just the 2 possible probabilities, we go multiply all of them to the power of the number of counts we got for each of the outcomes. Remember, here was heads to the power of the number of times I got heads, times the probability of tails to the power of the number of times I got tails. Here is going to be the same thing, but extended to the k possible outcomes. And instead of the binomial coefficient here, we are going to have the extension again, in where we will have the n factorial, meaning the total number of flips, and below each of the quantities factorial, right? Okay, so this is the way we map the binomial to the multinomial. Again, we're going to improve our notation here. We will use this notation, much more compact, and same thing here. We'll use the product notation here as well. Okay, how we rewrite the likelihood? We know that the likelihood is this binomial, so at the end, the likelihood is going to be, using our new notation, this term, right? Just an extension of the previous likelihood to more outcomes. Okay, now what we need to do is to find the prior. Remember, we want the posterior predictive at the end, so we need the likelihood, the prior, the posterior, and then the posterior predictive. And the prior was a beta distribution, and the beta distribution was the distribution for our probability of heads. So how this distribution will look like for k possible outcomes? And remember that the beta function was this division between the gamma functions, right? With this property for the alphas. Okay, fortunately, there is one distribution that is just an extension of the beta distribution to more outcomes. That distribution is called the Dirichlet distribution. It's exactly the same equation, but extended to k possible outcomes and k possible hyperparameters alpha instead of just 2 as we had before. The same beta function, same product of the probabilities. And the definition of the beta function is the same. The division of the product of the gammas divided by the gamma of the sum of all the alphas. And again, all the alphas must be positive and all the thetas lie between 0 and 1. And they add up to 1. Let's visualize the Dirichlet distribution. For example, in the case of 3 possible thetas. Let's say we have a problem with 3 possible outcomes. We use this visualization, which is this triangle called the 2 simplex. And here, each green point is one vector that contains theta 1, theta 2, and theta 3. And the sum of them is equal to 1. And that's why we end up in this triangle that start from 0 to 1 on each of the axes. And the feasible points here are only the ones that are inside the triangle because they must add up to 1. So our Dirichlet distribution is going to be a probability assigned inside the triangle. For example, this could be a Dirichlet distribution in where most of the probability or mass is concentrated here in the middle. And we're going to have things like this one. Here, the mass is shifting towards theta 2. So in this case, theta 2 is going to be more likely than the others. So let's see more cases. I'm going to visualize the triangle now in 2 dimensions, but it's the same thing. Remember that the alphas were the imaginary counts, the parameters. So here we can play a little bit with the alpha. Let's say we have alpha 1, alpha 2, and alpha 3 in this vector here. As you can see, alpha 2 is way bigger than the others. That means that our imaginary counts for alpha 2 are higher. In other words, our prior should be higher for theta 2. And that's why this Dirichlet distribution has most of the mass concentrated in the corner of theta 2. This is another case. If alpha 1 is way bigger than the other 2, our prior is concentrated heavier in theta 1. And we can have, of course, all the combinations. In this case, alpha 2 and alpha 3 are slightly bigger than alpha 1, so then the mass is getting concentrated between the middle of both theta 2 and theta 3. And this is the case in where the 3 hyperparameters alpha are the same, so our prior or imaginary counts are not in favor of any of the outcomes. Then we have a fully centered distribution that is equally likely for all the thetas. Okay? So this is an example of how we can visualize the Dirichlet distribution for 3 possible outcomes. Okay, so our prior is going to be just the extension of the beta distribution to the Dirichlet distribution with these parameters. Okay, so we have already the likelihood in k outcomes, we have the prior, now we need the posterior. And remember that in the 2 outcomes case, in the coin example, the posterior was another beta with these parameters. And we obtained this posterior by multiplying the likelihood times the prior, divided by a constant. So by multiplying our likelihood times the prior, we have this equation. And analog to the 2 outcome case, this is going to be just another Dirichlet, but with updated parameters. It's going to be this equation. Another Dirichlet distribution, but instead of having just the n's or just the alphas, is going to be the sum of them, because it's considering the prior information plus the data coming in the n's. Remember that the n's were the sufficient statistics in this problem. And as you can see, this is a Dirichlet distribution of parameters alpha 1 plus n1 and so on. Okay, so we know our posterior for the k outcomes case. Now we need the posterior predictive. And remember, in the beta case, we obtained our posterior predictive by calculating this integral, the probability of our next flip given the parameters times the posterior. And this was this integral of the probability of heads times the beta distribution with these parameters, the ones that include the data and the prior parameters. So now we can just extend this to the Dirichlet case. So if we want to calculate the probability that the next flip is going to be the outcome m, for example, then it's going to be the integral of theta m times our posterior, which is the Dirichlet distribution for our theta parameters. And that's why our integral goes over our theta parameters, right? And the result is exactly the same result we got before. The sum of alpha m plus the number of times we got the m output divided by the sum of all of them. And again, as in the beta case, this matches the expectation of our theta m parameter in terms of the posterior distribution, exactly what we got in the two outcomes case.